For the next examples that we're going to work to finish them out today, we'll be working in the normal and tangential coordinates, and we talked about that last time in class. So let's see what our first example is, and it's the swing problem. And we talked about the swing problem briefly in class. Take a look at the picture. Notice theta, the swing angle, is measured from the horizontal. Let's zoom in as much as we can and attempt to read the problem statement. The girl has a mass of 40 kilograms and a center of mass at G. We'll look at that in the picture in a moment. If she is swinging to a maximum height defined by theta equals 60, determine the force developed along each of the four supporting posts, such as AB at the instant theta equals 0. The swing is centrally located between the posts. Okay, so 2 points in time. Girl at the high point, 60 degrees. And the second point in time would be girl at the low point. We're going to want to determine the force in the beams. Looking at the problem statement, or at the problem, the force in the beams, if we ignore their weight, will come totally from the force in the rope. If when we would cut the rope, as I've suggested many times, and we want to find the rope tension out of the dynamics, then the rope tension will lead us to the statics of finding the forces in the legs. And we want to find the rope tension at the 0 spot. That is the spot where the rope tension is greatest for two reasons. Because gravity is aligned with the rope, which maximizes the gravity portion that the rope carries, but the girl is also traveling the fastest at this bottom point, having a maximum centripetal force, which has to be countered by the rope. Now, the difficulty with this problem is it is not a constant acceleration. So as we travel from the starting position to the final position, acceleration is not constant. And what we need to do is figure out the velocity right here, because we're going to be dealing with a normal force, and that normal force will go right into the rope. And we need v squared over rho. Rho is no problem, but we do need the velocity of the girl right here. And since acceleration isn't constant, we can't use those equations to find the change in velocity. We're going to have to integrate. So here we go. Looking at a free body at any angle theta, not just 60, not just 0, at any angle theta, we will have gravity acting straight down, and we'll have the tension force acting along the rope at the angle theta. And if we sum forces in the normal direction for any angle theta, we will have a tension, all of it, acting in the normal direction pointing inward, and we will have a component of gravity, mg cosine of theta, and that component of gravity would be acting here, but that would be in the negative of the normal direction. Okay, so sum of forces equal mass times acceleration in the normal direction, which is v squared over rho. Plugging in theta to this equation will give us our maximum tension, and our maximum tension is mv squared over rho plus mg. They add up. And we know that the maximum V will occur at theta equals 0. So V max at theta equals 0 will give us our maximum tension. We still don't know the velocity. How will we get there? We're going to sum forces in the tangent direction, because velocity increases in the tangent direction, and we can deal with the acceleration in the tangent direction. So sum of forces in the tangent direction, looking at the free body diagram, is only a component of the weight, and that acts in the positive tangent direction. And so we have mg sine of theta, that component in the tangent direction, is equal to the mass times the acceleration in the tangent direction. Canceling the mass on both sides lets us say that the acceleration in the tangent direction is g sine of theta. Now, clearly acceleration is not constant, depends on theta, which depends on time. Okay, but that doesn't shut us down, because we can integrate non-constant accelerations. We'll use the ADS equal VdV form to integrate. And so we will integrate VdV from 0 to Vmax, and we will integrate our tangential acceleration, which we'll replace with g sine of theta, and this ds we're going to have to turn into a d theta quantity. And so the next step then, where did the rest of that problem go? Here it is. So we are going to say, and I probably need to zoom out a little bit. See if I can get her to zoom out a little bit. There we go. Okay. Because we're traveling on an arc of a circle, the length of the circular arc is the radius of the circular arc times the angle of the arc. So ds is equal to a minus r d theta. Now let's take a look at y minus. As the girl travels forward, and we're considering the tangent direction here, so down is forward. As the girl travels forward, does theta get bigger or smaller? And the answer is theta gets smaller. And since theta gets smaller, an increase in s causes a decrease in theta. Therefore, we will take that into account with a minus sign right here. That's one of those direction things which would cause you to change the sign. So now we have the integral from 0 to Vmax of VdV. Now our variable of integration is theta. So our limits here have to be theta type terms. And so we will integrate this thing from a starting value of theta down to theta equals 0, which is our stopping value. And the starting value of theta was 60 degrees. But we're going to just leave this in as a generic theta for now, so we get an equation of velocity as a function of how high we started to swing. This side gives us a Vmax squared over 2. Integrating the sine of theta is going to give us a negative cosine term, and so we're going to get a positive gr cosine of theta. Integrating from the starting theta down to theta equals 0, and plugging that in, we will get a gr cosine of 0 out of the top term, and we're going to get, and the cosine of 0 is 1, and then we're going to get a gr cosine of theta out of the bottom term. So this becomes a gr times 1 minus the cosine of theta. And so we've got our maximum velocity as a function of theta, and we're going to go with 60 degrees, and so we plug in pi over 3 if we have our calculator in radians, or 60 degrees otherwise, and we get Vmax squared of 19.62. We could actually take the square root and solve for Vmax, but in our next formula we're going to need Vmax squared, so we'll just leave that alone. Okay. And so, knowing Vmax, we can go back to our earlier equation for maximum tension in the rope. We know the mass, we know the radius, we now know velocity squared, and we know the weight, mg. Plugging all of that in, we get a maximum tension of 784.8 newtons. And now we understand that that will come through the rope. And then we'll have two leg tensions on this side and actually they're in compression. Two leg forces on this side, two leg forces on this side. This is just a statics problem which says sum of forces in the y direction equals 0. And notice our coordinate system y is positive. And so we'll have two f's times the cosine of 30 degrees acting upward, and we'll have Tmax acting downward, plugging in our value of Tmax of 784.3 and handling the trig. We get a force in each leg of 227 newtons.